had to be a good breezy and change your predictions.
So the way that I think about it is that human intelligence has been shaped by a set of constraints that human minds operate under, and those constraints are quite different from the ones that are faced by intelligent machines, right? So if you think about what's characteristic of human intelligence, all of the things that we learn from the data which we're going to experience in the course of a single human lifetime, right? So that means that we're intrinsically limited in the amount of data that we can learn from, right? In order for something to be useful to you, you probably need to learn it relatively early on in that lifetime. So, realistically, we're talking about, maybe 20 years of data that you're you're using to form most of the inductive inferences that you're going to make about the world that you live in, right? And even much of that happens in the first 5 years, right? Like we learn language pretty well in the first 5 years of life. We've kind of figured out most of the causal structure of our environment, although we're still fine-tuning it after that, right? We kind of got most of the stuff that makes us a human being in those first 5 years of life. Okay, so that's thing number one, is limited data. That's something that shapes human cognition, is that you have to take about 5 years to figure out all of this stuff. The second is that we do all of that learning and all of our thinking with a fixed amount of compute, right? Which is what you're carrying around inside your head, 2 to 3 pounds of neurons, right? So that means that, way number two that we're different from our AI systems, right, is that we have to use that same amount of compute for every single problem that we solve. And so we need to be efficient in the way that we use those computational resources. We need to be able to recognize when a problem has the same kind of structure as one we've seen before. We need to be smart about how much time we spend thinking about any one particular thing. And so we need, something that allows us to make good use of those limited computational resources. So that's number two. And then number three is we have limited bandwidth for communication, right? So if it was just possible for me to transfer my brain state to you, then we could easily overcome those limits on data and computation, because I could just, share with you all of the data that I've ever seen, all of the conclusions that I've drawn from it by computing on those data. If we needed to work on a problem that was too hard for one of us to solve, we could just combine our computational resources. That would allow us to overcome those constraints. Instead, we have to do this by doing what we're doing right now, making honking noises at each other, right? And that is a really low bandwidth method of communication. So humans have developed all sorts of workarounds for this, right? We've developed language that allows us to convey complicated concepts to one another, teaching as a means of compressing information. Like all of the data that I've seen, you don't need to see, you just need to have the information from me about what to conclude from it. We develop methods for creating social institutions, things like science, that allow us as a community to aggregate knowledge across generations, engage in what's called cumulative cultural evolution. All of that stuff is stuff that allows us to, try and overcome those constraints, but it's still not as good as if we had sort of perfect high bandwidth communication. Okay, so by contrast, the current approach that's taken in AI is one of scaling the amount of data that's going into systems. So it's many, many human lifetimes of data that these systems are now trained on. It's scaling the amount of compute that's going into those systems, and you can kind of have arguments about how that compute compares to human minds, right? But the relevant thing is that that number is something that's easy to increase, whereas for humans it's not. And you have the potential for just being able to transfer states between machines directly, right? So you don't have to worry about those low bandwidth communication bottlenecks that are characteristic of human cognition. And so for that reason, we might expect that human intelligence would continue to be quite different from machine intelligence, because it would be nice to have machines that could learn from less data and be more efficient in the way that they use computational resources. But if you just want to make a machine that does a particular task, and in particular, if you want to be the first person who makes a machine that can do that, then you can kind of get around all of the hard engineering that might need to go into producing a system that has good inductive biases for solving a problem, or producing a system which is able to be resource efficient in doing that. And that's kind of the mode that we've been in for AI, is really just turning up that knob of data and compute, because it's the thing that so far has been the easiest way to get us to more effective AI systems.
Okay, and so I'm wondering. So two main things I'm wondering. So trying to order my thoughts. First one is, then if I understand correctly what you're saying, you're mainly saying that the way we're going to be able to make these generative AI learn is going to be different from the way our brains learn. Does that mean you think there is something we can do so that we build these machines, these generative AI, in a way that's complementing our learning and even helping our learning and maybe, fast tracking it in some way? What kind of potential do you see here? Also, what kind of drawbacks are you trying to maybe avoid? Because we are building these machines, so we are in a position where we can also try and avoid costs that we can anticipate.
Yeah. So I don't think there's anything intrinsic to the way that AI is currently being built which has that kind of human compatibility built into it, right? The two things that I think are properties of the way in which AI systems are currently trained that do contribute to this to some extent are, first of all, training on language, right? Or other data which are human-generated data. That's something which means that these systems end up kind of like viewing the world in the same way that we do, because they're viewing it through the lens that we provided, right? So if you think about what language is doing, language is one of those mechanisms that humans developed as a means of overcoming that limited communication bottleneck. And as a consequence, it's a thing that we use to describe the world around us in a very compressed form. And so that compressed form, as well as the structure of language itself, is something which, when you put it into an AI system, means that that system actually gets a lot of knowledge about the world that's being digested through human minds, right? And so that's one thing that maybe stops these systems from being quite as alien as they could be, is that they are really sort of like trained to view the world in the same way that a human has. The other thing is the last stage of training for many AI models is something called reinforcement learning from human feedback, right? RLHF. And that's something where humans give direct information about the preferences that they have about the responses that a system is producing. And that's something which in some ways contributes to alignment between humans and machines, although we have a recent paper where we argue that, in fact, what it results in is more alignment between the current state of knowledge that humans have and machines, right, which is not necessarily the same thing as having the human's best interests in mind as you go further into the future. And you can think about this even in simple examples, like if you're building a chatbot that is going to advise you on what products to purchase, unless that chatbot is receiving its reinforcement based on how satisfied you are with the product, after you've bought it, right, then it's going to be incentivized to instead focus on giving you the information that makes you satisfied at the point where you make the purchase. And that is not the same thing. And it's not the same thing in a way that can, lead those models to intentionally, well, we shouldn't say intentionally because it's not an intentional agent, but to engage in behavior that, a human being would consider deceptive. And so I think if you really want to build systems that are designed to interact with people, then there's a lot more things that we could do which are making direct use of the things that we know about people. So we've done a bunch of work on what we call representational alignment, which is making sure that the representations that the models have are the same as the representations that humans have. And so in some early work, we actually showed that if you train a vision model on, instead of training it on sort of sanitized data, where every image has a label which is the sort of agreed upon label that the humans give it. If you train those models instead on data that contains human errors, where when the humans are confused, you include those labels too, the models actually end up with better representations and representations that are more aligned with those of people. So that's something where having this more complete information about how humans see the world and the kinds of things that humans find confusing actually lets the model get representations that are more human-like. And in other work, we've shown that models that have more human-like representations actually do a better job at things like learning from small amounts of data, and at learning to capture human moral judgments, right? So if you view the world in the same way, that gives you a better basis for being able to, feel the same way about the world in terms of what's a good action to take versus a bad action to take. And we've done other work where we talk about a more general idea of conceptual alignment, which goes beyond just sort of having these representations that we can measure in terms of what's inside the model that align, and really being focused on this notion of like understanding the world in terms of the same basic concepts. And so even when we have models that sort of correlate in their representations, they can still be quite different in the way they're making sense of the world. So for example, humans think about the world in a way where we distinguish between different numbers of objects, right? Where the number of things is the sort of discrete thing that we represent and we can individuate. And it seems like, at least if you take image models, once you get past 4 or 5 or 6 objects in an image, they kind of lose track of what those numbers are. So they just sort of have, like maybe have somewhat individuated representations of small numbers, but they just have sort of like a fuzzy mass when you when you get beyond those small numbers. And that's exactly how part of human cognition works, right? If I show you an image and I ask you how many things are in it, if there's up to 4 things in the image, you're going to be able to answer it perfectly, and then after that you drop off. But we have this other richer conceptual representation which allows us to individuate higher numbers, 30 and 31 from each other, and so on. And so at the moment, our AI systems are capturing sort of part of how humans perceive the world. It's kind of like the part that happens very quickly, that you're able to do in less than a second, where you're just sort of like seeing something and making sense of it, or sort of like reading something and getting the gist of it. But they're missing something, which is the more symbolic, abstract representations that people form. And so we have a paper called Machines That Learn and Think with People, where we make this argument, and so to say, if you really want to make machines that are able to engage with humans in all the ways that humans engage with humans, then we need to capture more of the kind of thing that allows humans to engage with humans, which is having these shared representations of the world. And that's probably going to require some innovation in terms of the methods that we use for building these AI systems.
Yeah, okay, that's so fascinating. I'm curious. So my main, one of my main questions in these is, how can we apply what we learned basically so far about human biases and cognition to make these generative AI assistants basically elevate us and help us try and not fall into these biases that may be conscious and unconscious, but we know about them from research. How can we make that happen? Because what I'm thinking is, if we're trying to make them to our perfect image and symmetry, that's useful, but I think we would be missing one of the most interesting parts, which is trying to make us better humans instead of just the same we are. And so, is that possible? Is that something the research is currently going towards? How hard is it? It's like it seems like a huge endeavor to me.
Yeah, I mean, my first response would be, for the reasons that I said, it's not clear to me that an objective should be building AI systems that are like people, because people, like,
I agree.
What human minds are is a consequence of this evolutionary process, right? That reflected various biological constraints that we operate under, and it might be better to think about it in terms of, what's the best way for us to build intelligent systems that aren't like people, in terms of what's easy for us to engineer, but also something that's easy for people to interact with, right? And I think that's a perfectly reasonable goal for AI, right? So, if you think about, birds and jet planes, which is an example that people who work on AI talk about a fair amount, right? So, you studying how birds fly is incredibly important to making your first airplane, right? In terms of like understanding aerodynamics and lift and all of these fundamental concepts that are intrinsic to like how you're going to design the wings of, your plane and sort of figure out like what it is that actually makes something fly. But there's a point where once you have something that's flying, you can engage in an iterative process, which, is the one that leads you to jet planes, right? And jet planes and birds are very different from one another. And I think that's a totally reasonable place to end up, right? I'm not going to be someone who's going to be like, we should build flying machines that are more like birds. There are plenty of reasons why, you might want to take some more bird-like properties and put them into jet planes. For example, being more efficient in their fuel consumption, or other kinds of characteristics that birds have. Birds are sort of amazing as examples of flying machines, right? But it's not something that, if your fundamental goal is I want to get from one location to another as fast as possible, that's something where, like learning more about like jet engines is probably the way to go, right? And I sort of feel like we're in the same space with AI. It's like, yes, there's plenty of things that we can still learn from human cognition, but we shouldn't, say that our objective is to build something which is, human-like necessarily. So that said, there are plenty of ways that AI can be helpful to humans. So one of the things that I work on is understanding human decision making, and this kind of goes back to those experiments by Kahneman and Tversky that I talked about before, right? So part of what they showed was that not just people are bad at reasoning about probabilities, but people are bad at making decisions with respect to, expected utility theory as our kind of criterion of what it means to be a good decision maker. And that's certainly true. And if we try and think about that in terms of the different levels of analysis, right? Expected utility theory is our abstract computational level theory. It tells us what we should be doing. But there's a sense in which that is a kind of theory which, in fact, could not be achieved by any real entity that exists in the world, right? So expected utility theory says no matter how many outcomes you have, for each of those outcomes, evaluate the utility, evaluate the probability, take the expectation. If you're trying to use that as a guide to making any real decision, it's kind of impossible to do that, right? Because, you'll just spend your entire life thinking about possible outcomes, trying to evaluate how good they are, trying to evaluate how probable they are. And in fact, most of the time when we have to make a decision, we have to do it under some kind of time constraints. And so those constraints are things that are intrinsic to the way that the problem is set up. They're also a consequence of that sort of second level with the kinds of algorithms that we're able to execute on our human brains, right? And that sort of gets us down to the third level. So it's, things from these other levels of analysis that are influencing the problem that we should be thinking about. And so back in the 1980s, some computer scientists who are trying to figure out how to make a good AI system, so like Stuart Russell and Eric Horvitz, among others, they tried to work out, well, what's actually the right optimization problem to set up for making a decision? And they came up with an idea that they call bounded optimality. Basically, the idea is that a bounded optimal agent is one that uses the best possible algorithm for making a decision, taking into account not just the outcomes that produces, the sort of expected value of those outcomes, but also the computational cost involved in executing that algorithm. And that's a much more realistic way of thinking about how to characterize optimal decision making. We've used that idea and expanded on it in an approach that we call resource rationality, which is the idea that actually being a rational agent means making rational use of the limited cognitive resources that you have to do the best that you can in making the decisions that you make. And we can use that as a lens for then going back and reevaluating human decisions. And when you do that, you find out that a lot of the things that people do that deviate from expected utility theory are actually things that kind of make sense from the perspective of resource rationality. Like the heuristics that people use for solving problems are typically good heuristics when evaluated by this criterion of, do they, achieve relatively high expected utility while, not incurring too much computational cost. But the other thing that you get out of this is a perspective on how you can help humans make better decisions, which is that if we're making bad decisions some of the time because of those resource constraints, one way that we can better support human decision making is by increasing the computational resources that are available to human agents. And so, Elon Musk is trying to do that by putting chips in people's brains. That's not where we are in this space. Instead, what we focused on is, what if you can use AI systems to put more compute in human environments, right? So that when you are making a decision, we've sort of partially pre-solved part of that problem, and we can give you information in a much more accessible way that's going to help you make a good decision. So either putting the most relevant information in the most easily accessible place, or giving you information about payoffs that supplements, the information that's immediately available to you, sort of gamification, right? Where we're saying, you get some more points if you, choose this option, right? Where you can actually set up those points in a way that better aligns with people's long-term goals, right? Like one of my collaborators, Falk Leader, has worked on making gamified to-do lists where you can specify the things that you want to do and how valuable they are, and sort of break these down into components, and then it sort of automatically works out how many points you should get for doing each thing. And that gives you a kind of much more immediate reward for like checking something off your to-do list as those points add up, and maybe you get yourself, some prize when you get enough points. And that's a way of sort of like helping to motivate humans who, might not be able to plan all the way to the end of some long-term goals. And we've actually run experiments. We've shown that this kind of thing can help people reduce procrastination. So those are ways of using elements of AI systems to help humans without having to go all the way to like building something which is, a human-like AI.